In these notes, we're going to go over the combined gas law. The combined gas law combines Boyle's law, Charles' law, and Gay-Lussac's law to give a relationship between pressure, temperature, and volume when one of those is not constant. In order to use Boyle's law, Charles' law, or Gay-Lussac's law, you would only be showing the relationship between two variables, given that the third is constant. The combined gas law allows you to look at what happens when all three change. There's actually one variable that does not change in all four gas laws, including the combined gas law, and that would be the amount of gas, represented by the number of moles of gas. Before we look at any more word problems, I want to look at something called standard temperature and pressure. That's because sometimes in the word problems, they won't actually give you the numbers that you need, but instead they will just tell you that the gas is at standard temperature and or standard pressure. Sometimes they may even use the abbreviation STP. So you should know anytime they say standard or use the abbreviation STP that you have these given numbers. These are the temperatures and pressures for standard temperature and pressure. The standard temperature is 273 Kelvin, which is equal to 0 degrees Celsius, so we're at the freezing point of water there. And then the pressure is just the normal pressure, so 1 atmosphere. Sometimes the word problems seem tricky because it seems like they don't give you enough numbers, but you always have these numbers in your back pocket. You've just got to look for the word standard or the letters STP. So this is the formula for the combined gas law. Let's look at the fraction version first, and then I'll describe how that becomes the more linear version. The first thing that I want to point out is how we can find all three gas laws within this formula. Here I have highlighted Boyle's law, P1V1 equals P2V2. Next I have highlighted Charles's law, the direct proportion between volume and temperature. V1 over T1 equals V2 over T2. And finally here I have Gay-Lussac's law, the direct proportion between pressure and temperature. P1 over T1 equals P2 over T2. Now I know fractions aren't everyone's favorite thing, so the first thing that I want to do to this formula is to get it out of fraction form. So I'm going to cross multiply. P1V1 would be times T2, and then P2V2 would be times T1. So using this more linear version is what I'm going to do in the notes. You just got to be really careful that you know your temperatures are kind of flipped. The combined gas law is great for being able to handle a change in all three variables, pressure, volume, and temperature. Just keep in mind that the amount of gas would still need to remain constant. Let's look at our first example. I see another word problem. So the first thing I always do to word problems is try to focus on the numbers. I want to look for my variables which will have numbers with letters after them, like this 985 torr. Torr is what we call a unit, letters that come after the numbers. We also have here 27 degrees Celsius and 105 liters. Those are the only actual numbers that I see. But we had like 6 variables in the combined gas law, so where are my other numbers? We are going to have to read a little bit more carefully. A sample of neon gas occupies 105 liters, got that one, at 27 degrees Celsius, got that one, and under a pressure of 985 torr, got that one. Where's my other set of numbers? It asks what volume, that must be my unknown, would it occupy at standard conditions? That's the key right there. Whenever I have standard conditions, I know what the temperature and pressure are. I know that the temperature is equal to 273 Kelvin, and I know that the pressure is 1 atm. Those are my other numbers. What I don't know is the volume with that set of information. I have my other set of information, the temperature, pressure, and volume that were given in the first place, in the first sentence. The temperature was 27 degrees Celsius. The pressure, torr is a unit for pressure, so it's going to be 985 torr. And then the volume was the 105 liters. I also know that this first set of numbers goes together, so let's make that T1, P1, and V1. And I know the STP numbers go with the unknown, so we'll make that T2, P2, and V2. The next thing that I want to look at is the units. The first big red flag that I see is degrees Celsius. I already know that I cannot use degrees Celsius for gas law problems. So I'm going to take my 27 and I'm going to add 273 in order to get the Kelvin temperature of 300 K. Now when you add, you go by decimal places. So I am going to put a decimal at the end of the 300 to show that all of those figures are significant. 300 decimal Kelvin. I actually see one more big problem. P1 was given in torr, but we wrote down P2 as 1 ATM. If I try to use two different units in a problem, I won't be able to cancel them out. You have to make sure that your units match before you plug them into the formula. The easiest conversion to make right now would be from ATM to torr, because I know that 1 ATM is equal to 760 torr. It was one of our conversion factors. So if I just use 760 torr for P2, that would solve the problem. Now that we have all of our variables identified, I'm going to copy down the formula, but be very careful that you flip the temperatures. P1 V1 T2 equals P2 V2 T1. Next, I want to start plugging in my variables. First, I have P1, so I have identified P1 as 985 torr. That'll be the first thing that I copy down. Then I have V1, which I identified as 105 liters, so I put that in next. Careful with the temperature. This is T2, which was my standard temperature of 273 Kelvin. So I have those three variables on the left. Now for the right side. P2 was my standard pressure, which we converted to 760 torr to match the 985 torr. Next is V2, which we actually don't know. So instead of using X with gas laws, we're just going to let them be the variables that we are trying to solve for. So I'm just plugging in V2, treating that like my X as my unknown. And then last I have T1, which goes back to the given, the original initial temperature, which we converted to 300 Kelvin. The next thing I'm going to focus on is the algebra. How do I isolate V2? So I right now have V2 multiplied by 300 and 760, so I'm going to divide both sides by both of those numbers in order to isolate V2. So on the right hand side, 760 torr cancels completely and 300K cancels completely. On the left hand side, it's just the units that cancel. Torr cancels with torr and Kelvin cancels with Kelvin, meaning the only unit left is liters. So I know liters will be my unit, and all I have left on the right hand side is V2. So now I need to do the math, the calculator work. So I would type in 985 times 105, enter, times 273, enter, divided by 760, enter, divided by 300, enter. You want to hit divided by in front of all of the numbers that are on the bottom. Another way you could do this would be to multiply your top numbers, then separately multiply your bottom numbers, and then you would divide those two answers. Just be really careful with order of operations. You don't want to end up multiplying the result of the top by the 300 on the bottom. The result you should get is 124 liters for V2. The significant figures for this one are a little tricky. One thing you should know is that when we use STP, those numbers do not limit our significant figures. We treat them as exact numbers. So the significant figures are going to come from the given numbers. The other thing that's really tricky here is the temperature is actually 3 significant figures. Because we converted it to Kelvin using decimal addition rules, that decimal is there on purpose meaning that that temperature has 3 significant figures when we use it in the problem. And so we use 3 significant figures as the guideline. They all have 3 significant figures, so does my final answer. On to example 2. Another word problem, so the first thing I'm going to do is go through and look for my numbers that have units after them. A sample of gas occupies 10 liters. There's one. At 240 degrees Celsius, found another one. Under a pressure of 80 kilopascals. There's a third number. At what temperature would the gas occupy 20 liters? There's a number. If we increase the pressure to 107 kilopascals. So now I've identified 5 numbers. The thing that I'm going to be looking for here is temperature, so that would be my 6th variable. The next thing that I want to do is group them. What are the temperature, pressure, and volume that go together as my initial set? That would be the ones that come from the first sentence. The 10 liters, the 240 degrees Celsius, and the 80 kilopascals all exist simultaneously. That's our starting point. So that's what I'll use for T1. The temperature is a degrees Celsius, 240 degrees Celsius. Kilopascals represents a pressure, so I'm going to use 80 for P1, kPa. And then liters is a unit for volume, so 10 liters must be my volume. My second set of variables, T2, P2, and V2, would come from my second sentence. At what temperature? So I have an unknown temperature. 20 liters. Liters is a unit for volume, so I'll use that for V2. And then kilopascals is a unit for pressure, so 107 would be my P2. Before we move on to use the formula, we want to double check our units. I see a red flag here, degrees Celsius, the biggest no-no in gas laws. So the first thing that I want to do is convert that to Kelvin. So I'm going to take 240 and I'm going to add 273 to get 513 Kelvin. So that's what I would use for my T1. I also want to check that the other units match. I see kilopascals is the unit given for both pressures, and I also see liters given for both volumes. So since everything matches, and I'm already in Kelvin now, I'm going to go ahead and move into the formula. When you copy the formula down, again, be careful that you flip your temperatures. P1, V1, T2 equals P2, V2, T1. Next, I want to carefully plug in my variables to the right spot given the formula. So the first letter in the formula is P1. I know P1 is 80 kilopascals, so I plug that in first. And so on and so forth, just like we did in the last one, so that everything is in the right place. Be really careful with your temperatures, though. You have T2 on the left, that's our unknown. But you have T1 on the right, which was our given. They are flipped. So we carefully plug in every single variable to the right spot. Make sure that you carry all of the significant figures and all of the units to get our algebra ready to go. Once I've got it all set up, I'm going to try to focus on how to solve for T2. So the first thing I want to do is isolate it, and I'm going to do that by dividing by the 80 kilopascals and the 10 liters. So on the left-hand side, the 80 kilopascals cancels completely with 80 kilopascals, and 10 liters cancels completely with 10 liters. So the only thing I end up with on the left-hand side is T2. On the right-hand side, it's only the units that cancel. So kilopascal cancels with kilopascal, and liters cancels with liters, meaning Kelvin would be the unit for my final answer. Now it's time to pump this into the calculator. Again, just be really careful of your order of operations. The way that I would do this is 107 times 20, enter, times 513, enter, divided by 80, enter, divided by 10, enter. And you should get 1,372 Kelvin. And for sig figs on this one, technically all the numbers that we used had 3 significant figures when they were given to us, even the temperature. So we're going to round this a little bit to 1,370 Kelvin for our final answer. On to one last example. First thing I'm going to do to this word problem is find those numbers. A sample of oxygen gas occupies 23.2 liters, that's a number, at 22.2 degrees Celsius, there's another one, and 1.3 atm, found another one. At what pressure would the gas occupy 11.6 liters? There's another number. If the temperature were lowered to 12.5 degrees Celsius, last number. So I do have 5 numbers. My 6th variable would be what I'm solving for, and it does say, what's the pressure? There is an interesting catch on this one. It specifies that it wants the units to be millimeters of mercury for the final answer. Notice that the other pressure is in atm, so that is a problem we're going to have to address. Let's start by grouping them. It seems that the 23.2 liters, the 22.2 degrees Celsius, and the 1.3 atm exist simultaneously. The first sentence presents this as the initial conditions of this oxygen gas. Liters is a unit for volume, so I'll use 23.2 liters for V1. Degrees Celsius is a unit for temperature, so I'll use that to get T1, 22.2 degrees Celsius. And then atm is a unit for pressure, so I'll use 1.3 for P1. In the second sentence, we have our final conditions. We're solving for the pressure, that is our unknown. The 11.6 liters would give a volume, 11.6 liters, and again, degrees Celsius is temperature, so we'll use that for T2, 12.5 degrees Celsius. So I have my associations. The next thing that I want to do is check for my units. First red flag you should always look for, degrees Celsius. We know we can't solve gas law problems in degrees Celsius, so I need to convert both of these numbers to Kelvin. To do that, you add 273 to each number. So that gives 295 K for T1 and 285 K for T2. For significant figures, whenever you add, you go by decimal places. 273 has ones place as its last decimal place, so we're rounding the Kelvin temperatures to the ones place as well. Now I want to check the units on my other variables. Volume was given in liters for both volumes. V1 and V2 both come in liters. Since they match, I know that that's good. If I look at pressure, P1 was given in atm, and P2 is my unknown. The problem is, we specified in the question that it's supposed to be in millimeters of mercury. So I'm going to go ahead and change P1 to millimeters of mercury. That way when I solve for P2, it will already be in millimeters of mercury as it was requested. Now I want to focus on how to convert 1.3 atm into a number with millimeters of mercury. So for that, we're going to need dimensional analysis. With dimensional analysis, you always start with your given, 1.3 atm in this case, and put that over 1. That'll keep 1.3 in the numerator. Whatever unit you start with always goes to the bottom of the next conversion factor. So atm will also go on the bottom. We're trying to convert to millimeters of mercury. So I'm going to put millimeters of mercury on the top. We need a conversion factor. 1 atm is equal to 760 millimeters of mercury. Conversion factors are made up of things that have different units but equal each other. For example, 1 hour equals 60 minutes. You could use 60 minutes over 1 hour or vice versa. So for this conversion factor, I'm using 760 millimeters of mercury over 1 atm. So math-wise, I need to multiply 1.3 times the 760, which will give me 990. And if you look at the units, we put atm on the bottom so that it would cancel. The only unit that's left is the millimeters of mercury. So for P1, I'm going to use 990 millimeters of mercury. Now that I have all of my variables identified with the correct units, I'm going to copy down the formula. Again, be careful, T2 and T1 are flipped. Next, you want to carefully plug in your numbers. P1 and V1 get plugged in on the left, whereas T1 goes on the right. And then P2 and V2 are on the right, whereas T2 is on the left. And now it's time for the algebra. How do we isolate P2? I'm going to divide both sides by 11.6 and 295. On the right-hand side, 11.6 liters cancels completely, and 295 Kelvin cancels completely, leaving only P2. On the left-hand side, the units are what cancels. Liters cancels with liters, and Kelvin cancels with Kelvin, leaving millimeters of mercury as the only unit for my left-hand side. Now it's time for the calculator. Always be careful of order of operations. I would type in 990 times 23.2, enter, times 285, enter, divided by 11.6, enter, divided by 295. And you should get 1,936 millimeters of mercury. The significant figures on this one are a little bit tricky. At first it seems like all of the numbers that we used had 3 significant figures, but actually they didn't. 990 millimeters of mercury came from 1.3 ATM. That only has 2 significant figures. When we did the dimensional analysis and got 990, that doesn't change. You still have 2 significant figures. Conversion factors do not change your significant figures. So since the least number of significant figures in our givens has 2 sig figs, we're actually going to round this quite a bit to 1,900 millimeters of mercury. Worksheet 2 will give you plenty of practice on using the combined gas law. Submit a picture of the worksheet and your scratch work to the Dropbox when you're finished.